This is Physics 1102, exam spring 2023, exam 1 review. All right, and this will cover chapters, a little bit of chapter 14, but only as it applies to chapter 15. Chapter 15, this was temperature. All right. Chapter 15 is thermodynamics. All right, first law of thermodynamics, engine cycle, heat engines, efficiency, things like that. Chapter 16 on electric charge. And fields. And chapter 17. This is on electric potential and voltage. Voltage is about the best way to put it. And lab 1 on vaporization. Lab 2 on electric fields. And field hockey. All right, so that's what the topics will be covering for this exam. As far as here, so I'll go through each chapter briefly again. Again, look at the chapter review handouts, the PowerPoint, and such. Okay. For chapter 14, again, there's nothing specifically on chapter 14 being covered. The test is on 15, but just from 14, we have energy, internal energy is 3/2 nRT, right? Don't forget that. Where, you know, U is the energy, N is number of moles, R is a gas constant, T is temperature in Kelvin. So for chapters 14 and 15, we'll be using almost exclusively degrees Kelvin. So that's what we have there. That's the only thing really from chapter 14, because in chapter 15, all right, again, the equations we're covering there are his first law of thermodynamics, and this is delta U is Q minus W, where this is a change in internal energy, which comes from there, from chapter 14. Q is the heat added, and W is the work done. And this again is either in joules or calories. Both of them are interchangeable. Again, don't forget one calorie is 4.186 joules. Okay? So that's first part, chapter 15, I should say. Again, different processes, isothermal, Isobaric, isovolumetric, adiabatic, and okay, again, summarized in the table on table 15.1, which I've discussed in the lecture, as far as what the different processes are, what's constant. Again, iso means that that part is held constant, so thermal is temperature, baric is pressure, volumetric, so this is T, P, and V, and adiabatic, Q is a constant. All right, so that's what we have here. Then also we have the PV diagrams, which we talked about, and the kind of cycles and how you do work on a PV diagram. Because again, work is defined as P delta V, if P is a constant. Otherwise, that's what we have there as far as different kind of cycles, and I've gone through those on earlier. Second law of thermodynamics. All right. Second law of thermodynamics, again, heat flows from warmer to colder. So heat flows from hotter to colder. Technically go the other way around. So it goes from more order, to more disordered. And it could go the other way around, but we don't observe that to happen. And then again, efficiency of an engine, which is efficiency is work over Q hot, which is Q hot minus Q cold. So energy put in, energy that exhausted, divided by that times 100% as a percent. If we do it in terms of heat, that's what we get in terms of temperature. T hot, so we can measure the temperature of the incoming gas, in the system. The temperature of the gas exhausted divided by T hot times 100%. That's our efficiency of an engine. All right, we talked about that. I'm not going to get into refrigerators at all. That's not part of this class, or heat pumps. I'm just talking about that. And then finally on, as far as problems are concerned, we have entropy. And this order the disorder. And this is delta S is Q over T, where this is in joules, and this is in degrees Kelvin. So delta S is the change in entropy, and for all systems, it's going to be greater than or equal to 0. For most cases, it's going to be greater than 0, so we're leading to more disorder in that sense. So that's chapter 15, entropy in the second law of thermodynamics, and the problems with there. I had the problems related to temperatures of mixing. All right, so if you mix a warm water and cold water. All right, what is the change in entropy? Remember, we went through that lecture, and how one becomes just more disordered, the other becomes more ordered, but the overall change in entropy increases. So S1 plus S2 becomes S, delta S, which is going to be greater than 0. All right. So in any real system, the entropy always increases. All right, so that's chapter 15. Chapter 16. And I should say before I go on to there, it'll be approximately 15 to 20 multiple choice questions, similar to the review questions, and about 5 to 6 problems. Short answer problems. Again, the test will be online, and the date will be announced. Check the schedule. It'll be sometime first week, end of January, first week of February. All right, so, and then I grade these manually. All right, chapter 16. All right, electric charge. I've gone through this. All right, so again, definition of charge. We have insulators and conductors. All right, we have positive, negative charges, and we have Coulomb's law. Fe is K Q1 Q2 over R squared, where K is 9 times 10 to the 9th. And again, we compare this to force of gravity, which is G, the constant G, M1, M2 over R squared, where G is 6.67 times 10 to the minus 11. So we end up with this force of electricity. It's the same kind of expression, but instead of mass, we have charge. We have a constant, but it's different. Particularly, this is 20 orders of magnitude bigger. And so force of electricity is so much greater than gravity, but gravity still overwhelms because gravity is always attractive, while electricity, again, likes repel, opposites attract. So that's some examples related to that problem. We're only going to be doing problems in one dimension. We're not going to do any two-dimensional problems here as far as using Coulomb's law. So force between two charges. And again, electric charge, E is minus 1.6 times 10 to the minus 19th coulombs. Is the charge of the electron. Proton is exactly opposite of that. All right, then we got into electric fields. And we'll have things example again, electric fields, like, and what an electric field is if I have a charge, and if I put a positive charge near, which direction would that positive charge move? All right, so for a single charge can go out. For a dipole, minus and plus, it's going to be something like this. You know, your typical magnetic field. So that's what field is going to look like there. Again, it's a direction a positive charge would move. So in this case, it would be repelled by this one and then be attracted to that one. So this is electric fields. Right? And then moving on from there, again, we have field lines. We're only going to be doing two-dimensional surfaces. So again, these are some of the examples of dipole charges. If we have plus minus, if we have both positive, or if we have one is much greater than the other, or if we have a parallel plate where one charge is plus Q and the other is minus Q, electric field lines run parallel between the two plates. All right. So we have some problems related to those concepts. And that's about it. Yeah, I'm not going to do anything. Gauss's law, we're obviously not going to do anything. Oh, and then just the fact that if we have a conductor, electric field inside the conductor is 0, as we see here, which like why a car can be, you're safe in a metal car because any electricity that conducts it will flow around outside. So inside you're safe if you get struck by lightning. So that is all of chapter 16. And then the problems related to that. All right. So, chapter 17. All right. This is electric potential. And I should say, I think, we had a problem for force is K, Q1, Q2 over R squared. That's the force between two charges. But if we have to say single charge, Q1, then we define electric field 1 as F over Q2. All right? And so this becomes electric field 1 is K Q1 over R squared. So this electric field, which for a point charge radiates straight out. All right. Now, what we're going to do for chapter 17 is use the fact of introduce this term of voltage. All right, not velocity, but voltage, and this is units of, this is a Newton. You divide up by Coulomb. E is units of Newton per Coulomb, or it's also, we'll see, is volts per meter. All right, so we're going to define the volt. Okay. All right, so we're going to get into this term of electric, again, electric potential. We talked about if we have charge plus, again, minus, we have an electric field inside E, and if it's separated by a distance D in meters, the electric the voltage is E times D. So this is what we call a volt. And therefore E is V over D. So electric field is volts per meter. So we introduce the unit of volt. So what this means is, and this is in voltage, and what this, again, what we had is if we have a charge, put a plus charge here, it's going to get accelerated to the other side. So we put a plus some Q there. Then it will have a potential energy across of V times Q, which would be in unit of joules. So this is potential energy for parallel plates, as we talked about, much like we have potential energy of gravity, which is mgh. But instead of m, we got g and q. Instead of gh, we have v. So again, we talked about that. For a point charge, v is kq over r. So that's the potential in volts from there. And again, we're only going to be dealing with one dimension. And that's keeping that in mind there. So that's our expression for there, and that's our expression for voltage around a potential charge. Okay. Then capacitance. C, all right, for two parallel plates that have Q plus Q and minus Q, and a voltage between them, a capacitor, C is defined as Q times V. No. Q, C is divided as Q over voltage. So this is in units of what we call farads. Again, we talked about this, select your notes, or capital F. All right, so units of capacitance are in farads. So we have a capacitor, a battery is a capacitor, and so on. And for calculating capacitor of parallel plate, it's epsilon naught A over D. Now that's the area of capacitor, and D is the separation between them, and epsilon naught is 8.854 times 10 to the minus 12. And I don't know if we do any problems related to that. Storage of electric energy. Is potential energy is 1/2 CV squared, or 1/2 Q squared over V, depending on what you're given. 1/2 Q squared over C, right? And I believe that's the end of. We do have the lab related to electrocardiogram. All right, EKG. All right, so again, the characteristics of electrocardiograph. All right, the P, Q, R, S, and T portions of the graph, which we have for the lab itself. Okay. So again, exams, the lab exam is on, again, chapters